All right, so in this video, we are going to talk about adding numbers and then addition to SDLC. So as the first step to extend our language, we need to extend the syntax. So let's do that. And here we're just going to say we want to add numbers, and just for sake of time, have this typed and commented out to show them. So we are adding numbers, which really are of type nat, and we are allowing type nat to represent an expression. So here's a little bit of a spoiler alert that we're going to go and add addition later to our syntax. But for now, let's just first go through adding numbers. And once we have done that successfully, we will come back to implementing addition. And we will also add this coercion down here. Now, what this coercion does is we're telling our language that if somebody starts writing a nat in the middle of their program without using this constructor num, use this constructor to automatically turn it into a num. Next thing we are going to define is this notion of substitution for numbers, and expressions that perform an operation on numbers can really use this idea of substitution. But here we just have a number. So we really can't substitute a number with anything else. So when we are calling subst on numbers, we don't want any substitution to happen. So we are telling subst, when you see a number, replace it with itself. And next, we are defining a new type of value down here. We are saying not only these three things could be values, but we can also have another constructor of value n. And we are saying for all n, and n num could also be a value from here on out. The next thing we need to consider is this step part of our language, which evaluates everything in our language. But let's think about how numbers would fit into this. Numbers are already a value. So if we have something in our syntax tree that needs to be turned into a value, we can define them here to evaluate to a value, but we already have defined everything for values here, and adding a new type of value shouldn't really change our step. So we don't need to add anything to our step. It's already defined for all values. So we can just move on. So by just adding the value here, we finish the definition of our language. And next, we also want to update the proof system that helps us analyze the program or the programming language. So we are going to extend the type system. And now we have a new kind of type. We're just going to call it tnat for type nat. So this is all good with our lookup system. Doesn't really disrupt that. But we do have to extend our type system for SDLC. So to accomplish that, we have to say what happens when somebody types a number. And the way we are going to expand that here, I'm just going to put the comments down here because we're going to talk about add in a little bit. But for past type num, the way we are defining is that we are saying for all gammas and n's, we are saying that gamma shows us that num n has type tnat. And checking our work successfully, let's go to proving type soundness. So we would immediately get stuck here because we do not have a case for num, but this is somewhat trivial, at least for the free variable or is free variable fixed point. Since an expression will never be a free variable of a num, we can fix this and push it through. And this will go through the definition of closed, unstuck, and progress. So no problems there. All of those would be fine. And similarly for all other parts, if you just try to push it all through until the very bottom, it will work out. So we have now successfully added nats to our language. All right, so now let's attempt adding addition to our language. And to do that, we go all the way back up here. And what addition does when we are defining its type of expression is that addition takes one expression and another expression, given that num is also an expression, and then returns an expression. All right, and we also want to add special syntax for addition. So we're just going to define this plus sign to act as our addition operator in our language. And next, we have to update our substitution. Notice add is very similar to app in how it handles substitution, in that what we are saying is for each expression, if we can substitute it before we do the actual addition, we just have to substitute the right or the left or both of them if possible. Because if these are not values, we just want to substitute each side until they evaluate to a value, and then we can do the addition. And since this operation doesn't really add a new type of value to our value system, no pun intended, we don't have to change value. But on the other hand, we do have to extend step, and we have to add 3 types of steps or constructors here. So let's go through these cases. The first case is very similar to our app left case up here. And what we are saying is for all E1, E1 prime, and E2, if E1 can step to E1 prime, then add E1, E2 can step to add E1 prime, E2. Similarly, say that for V1, E2, E2 prime, if E2 can step to E2 prime, and we have value V1, then the addition or add V1, E2 can step to add V1, E2 prime. And finally, we say that if we had N1 and N2 such that N1 was a num, and N2 was also a num, and we had add N1, N2, both of type num, that can step into another num, which is the addition of N1 and N2. Now, next, we are going to extend our type system by adding a rule for addition. So let's just uncomment this and look at how that works. So what we are saying here is that for all environments gamma or G here, and inputs E1 and E2, if we can show that in that environment, E1 has type TNAT, and we can show that in the same environment, E2 has type TNAT, then we can show that the addition or performing add on E1 and E2 under the same environment will also have type TNAT. And next, we have to address the situation with free variables. And notice the case for add is again identical to the case for app. So that also works out. And then finally, the last thing that we have to fix would be to add a case for our addition inside the progress. And this is going to be very similar to the app case, which is up here, except there are going to be a few differences. Let's go through it. First, we destruct this IH has type 1. Next, we invert on our hypothesis. This is for any given environment, E1 is a TNAT, and also H1, which was, I think, a value E1. Then we destruct on the other IH has T by 2, and then we get 2 cases out. And for those, we can do inversion on H, inversion on H0, and then E auto. And then finally, we can invert on H1. Say there exists an E prime such that's an expression such that expression E1 can step to E prime in exactly 1 step, and then go to the right side of this goal and use E auto to finish the proof. And then now that this is through, assuming our canonical forms are also all right, and we can go all the way down over here and see if this would go through, and surely it does. So we have just added addition to our language as well.